Okay, it's a great honor to introduce Peter Zoller as our speaker for today. Peter is university professor at the University of Innsbruck. He actually did his PhD in Innsbruck and joined the faculty there in 1977 and spent most of his career there, with the exception of, I think, a very important 3-year stint, 5-year stint at Gilla and CU Boulder in the early 1990s. He returned to Innsbruck, and years later in 2004 founded the Institute for Quantum Optics and Quantum Information at the Austrian Academy of Sciences, and he was director there until 2020. Continued to work Berkeley and the IQOQI. Peter, I think, barely needs an introduction for the audience because he has done field opening work in so many areas of quantum science. But just to give a few examples, in I guess the early 1990s, shortly after Shor's algorithm came out, Peter had the seminal proposal for how one could actually start to implement quantum gates in systems of trapped ions that really kicked off the whole field of experimental quantum computing. A few years later, he pointed out that cold atoms in optical lattices could be a powerful toolbox for quantum simulation, namely simulation of covered models. He led a pioneering proposal for quantum repeaters and off the field of quantum networks. And he also has an early proposal for using Rydberg blockades to achieve quantum gates to neutral atoms, which of course is also a field that's exploding today. Though actually, I noticed his most cited work of all on Google Scholar is his very useful textbook on quantum noise. Okay, so some of the things I mentioned, I guess, date back for years. So I think I should also say that Peter continues to be very active in coming up with toolboxes for probing entanglement in experiments, ways of leveraging quantum simulators to study lattice gauge theories, optimal protocols for quantum sensors and clocks, and much more. And he'll tell you about some of his recent work. Today, before I let him do that, I'll just mention he's won more or less every award you can imagine, but just cite a few: the Dirac Medal, the Benjamin Franklin Medal, the Wolf Prize, the Havas Award of the OSA to German Physical Society, the Willis Lamb Award, and the Norman Graham Prize, the APS, a small subset. So we're very fortunate to have you here today.
Okay. Thank you, Monica, for this introduction. Thanks for inviting me here. I have to say that I'm having a great time here. I mean, this is a fantastic AMO community, and of course, much broader than I see here. So this is an incredible, place here to actually visit as an AMO and quantum optics person. So what I would like to do in my talk here today is sort of put the two keywords here that I guess are sort of very resonant with what's going on here. One is quantum simulation, the other one is the connection of quantum simulation with quantum metrology, using atomic platforms that include topics like that are down here: trapped ions, optical lattices, virtual arrays, polar molecules, and so on. And as Monica mentioned, sort of if I go back in my own history, I don't know, 25 years ago, we thought about many of these things as proposals, but with a certain vision behind it, being quantum computing or quantum simulation. But these things are now realities in the lab. And so very often the work that we're doing, that I'm doing at the moment, has to do with the fact that, that these machines that we dreamed up on the theory side, of course, fantastic experimentalists built and now sort of ready to play with to fulfill this kind of vision. So a lot of my work is now related to, well, here's a new idea, but why don't we try it out immediately? I should also add here that I'm somebody who always fell in love with these, analog quantum simulators or NIST devices, that we say, and we'll also see that during my talk here today. Of course, things are moving on. Now we have digital quantum computation and also quantum simulation. There are a lot of people interested in error correction. I also find this very interesting, but my talk today will be basically on these analog devices from the perspective of close collaboration with experimentalists. So the examples over here are examples of what we call programmable quantum simulators, scaling a very large number of particles, but of course not being universal computing devices. So let me now tell you a little bit of story about this programmable quantum simulators, but also in the context now of, for example, at the end, we're making them precision quantum simulators in the way that we're here. So here's sort of a list of topics that I'm interested in at the moment, and I decided here now to speak about work which is really unpublished, but you're in the middle of doing. I think that's maybe the most interesting part for all of you. I said one of them had to do with quantum simulation and metrology, and here are sort of systems that we were allowed to play with. Rainer Blatt, Christian Roos, Thomas Mons, they had a group in Innsbruck doing trapped ion simulators, computers, and so on. And we also had the opportunity to work with the Harvard, MIT, Aquera team to do, for example, quantum simulation of lattice gauge theories. And so a lot of this work is direct theory, but also that's related by the way to experimental work. So I will talk today at the very beginning about the project that we're doing right now, which is bounded error quantum simulation. I'll probably have to explain what I mean by that. And we do that via Hamiltonian learning and Liouvillian learning. So we're going to have quantum devices where we learn Hamiltonians, and there's a noise model, also Liouvillians, from the experiment back. And then we're going to use that in order to make a sort of precision statements, with bounded error for quantum simulation. I guess that's a new topic, and I will explain afterwards why I feel that this is sort of important and kind of a missing element in the landscape of quantum simulation that we have right now. And then sort of as an appendix to this discussion over here, I'll speak about ideas that have to do with what I call inverse quantum simulation, or I might also call it quantum material design. There's some ideas around that I would like to share, and we've been working on this for quite some time, and I think that we are coming out to the point where something meaningful is coming out, and this may be of interest to you. Of course, lattice gauge theories is another topic. Like the work that we did down here, we'll have only one slide at the end about it because I decided to talk about the new things here. And then we have quantum metrology, and of course here we have all of these ideas about building quantum networks and then use them for quantum sensing. I'm of course very much aware of the work also that's going on here in atom interferometry in the broadest context. So I'll tell you some ideas how we can use quantum quantum networks, built for quantum communication. Maybe also then there's quantum sensors, and to talk about non-local mass superpositions. You will see what I mean by that now in the following. So these are some of the topics I would like to cover. Well, I think that these systems here don't really need much introduction. I mean, there's this incredibly lively, AMO experimental community that builds all of these things. You can see I included the superconducting qubits here as honorary members in our AMO communities, because they are, of course, also have atoms, but they only have artificial ones, but they have atoms. And so the spirit between all of that is sort of very similar.
Tell us how you really feel.
And we have now ions, and this is, as I said, a system in Innsbruck that we are playing with. And when you look at these systems, sort of very much, if I talk to my, computer science friends, quantum computer science friends, they often look at these niche devices over here, sort of being very beautiful as illustrating certain phenomena. But I think it's also time, and this is what I will do in the first part of my talk, to think about them. Can we convert these experiments that are usually designed to see certain phenomena and not designed as high precision experiments to become a precision quantum simulator where these machines make predictions, with a bounded error and so on. So can we move them one step closer, even though they are sort of under code on the analog devices, to being quantum machines that might eventually even work in some regime of quantum advantage, to provide bounded errors. And we have some thoughts along these lines related to the Hamiltonian learning. That's what I would like to share. And there's some first experiments that I'd like to indicate. But let me mention first that I thought originally that I would speak more about this quantum simulation of lattice gauge theory. So we had some theory ideas, Daniel and also Thorsten in Innsbruck. They were postdocs in my group originally. We visited Harvard 2.5 years ago, came up then with ideas how to implement the phenomenon of so-called string breaking in lattice gauge theory with a tweezer arrays. And this was done experimentally at the Aquera company, and this took quite some time, but in the end it was very successful. So there's a paper now in print. Let me just tell you sort of what the phenomenon is here to contrast it afterwards. So I'll go to make precision quantum simulators. The basic phenomenon studied over here was that supposedly you have two charges. We call them plus Q and minus Q, and think of them as classical charges. There will be an electric field, of course, connecting them, and you quantize the whole thing. Then you have quantum electrodynamics. And if you make this string longer and longer and longer, you will store more and more energy into the string. But this thing being a quantum electrodynamics with matter, you will at one point create electron positron pairs from the vacuum. So this string will actually break, and this is a fundamental phenomenon also in quantum dynamics. When you have, of course, there are non-abelian gauge theory. Here we talk about abelian one, and we wanted to see that, and we designed a model where the so-called Gauss law that we have in lattice stage theory is implemented here by the Rydberg blockade. You know, there's been some ideas around there for some time, but we were able to do it now in 2D and come up with a model with a mapping and see these phenomena stand really live, both in static, you know, that we identify the corresponding phases, but also in dynamics that if you pull this string, you know, increase the string tension, you'll see this thing breaking up in the whole string dynamic that has an amazing agreement between theory and experiment. So I think it's one of these things where I say, wow, these analog simulators, they're really great. There's been parallel work by IQOQI, you know, doing a digital quantum simulation. This is really synthetic quantum matter here. But this was sort of on the topic of doing an analog simulation, a synthetic quantum matter, seeing for the first time in this context, at least, you know, this breaking string dynamics over here. But then we switch now to the first part and sort of this work in progress that I mentioned. And let me speak about Hamiltonian and Liouvillian learning in analog, but also it applies to digital. I will now talk about this part here. We have written papers about that, quantum simulation, and in particular about this bounded error quantum simulation. I think the main point is, from my side, really to get the idea across why I feel that it is important to do these kind of things, because I think that this is a bridge connecting what we do in analog simulation to the even more, you know, quantum computer and digital quantum simulation side of this whole story with our friends in quantum computing science. And of course, one of the reasons why we talk about bounded error over here is this, that we want to make quantitative predictions that are in this sense guaranteed quantitative. And eventually these techniques, not the experiments that I will show you following our regime, this regime of quantum advantage. And let me also say that there's prior work on our side, you know, like we studied not Hamiltonian learning, but entangled Hamiltonian learning and some systems, published some paper along these lines using random manufacturing toolbox. I will not speak much about these things here, but these are tool sets that were developed some time ago that we also now recite in the context over here. Okay, so my friends in Innsbruck have trap line experiments, and Manuel Stossi is one of the key people that I'm collaborating with. You know, all of you are probably familiar with trapped ions as being a 1D string. We shine lasers in, we have local addressing over here, and at the end of the day, what comes out from over here is this, that there's an analog simulator being realized that corresponds to the transverse Ising model, you know, with long-range interactions, see that this coupling J-I-J, and then we have some transverse magnetic field. At the end, we will ask the question now the following, that we want to do Hamiltonian learning to verify this thing in real experiment, maybe learn additional terms, which at the end we don't see. But then also in the limit of an XY model, where you just have to know an XX and the YY coupling over here in the regime of an effective large magnetic field that we have. So this will be kind of the prototypical model. And in this experimental context, we see able to do quench experiments where product states, whatever you want, you know, with very high fidelity, look at quench dynamics. In the earlier work, we have used this quench dynamic to design also variational circuits and so on. Doing measurements over here, and then from these projective measurements, you get your correlations, whatever you want. And the context now, the following, we will do the Hamiltonian learning as a black box learning in the real experiment. So this takes me then to this topic. So we're talking about Hamiltonian and Liouvillian learning and this bounded error quantum simulation. And the question is really the one, are quantum simulators, analog simulators, only good for sort of nice to see nice phenomena and maybe more qualitative level, or also as computational devices that we can trust the output in the sense of making quantitative predictions using techniques or methods that apply eventually also in this regime of quantum advantage. And this work is also sort of related in spirit what Ignatius Iraq has been doing. They wrote a series of papers to what extent analog simulators can sort of provably demonstrate quantum advantage. But we try to do these things sort of a little bit hands-on and then also in relation to an experiment. That's what I want to tell you in the following. And I already mentioned Metrology as the experimentalist, and these are the two people in particular. Tristan Kraft, who is a postdoc, borrowed from me, from actually Barbara Gauss. They are really a quantum, a theoretical quantum computing group, and not really sort of the AMO person that I am, but this has been a fantastic collaboration. So let me tell you what we want to do. So normal quantum simulation experiments always work like this. Well, there's an interesting, you know, target Hamiltonian over here. that your theorist friends give to you know as the one that you would like to implement. And then we do a simulation experiment, either being an analog like main flap over here, not digital, but we focus on this part over here. And then we predict certain observables coming out, and then at the end, plotting things that interest us, like maybe phase diagrams, whatever these things here might be. And of course, this is what analog simulation does. And the question is, can we trust these predictions of a quantum simulator? And so the way that we want to approach the problem is by this Hamiltonian learning, where we say, well, ideally, this quantum simulator over here, for example, I'm doing here quench dynamics, is we want to treat it as a black box. And fundamentally, you should ask the question, would like to do some sort of quantum process tomography, which is, of course, very expensive. But quantum simulation is sort of much simpler because, the Hamiltonians over here that are physically realized in a real many-body system, they are the ones that usually have maybe one body interaction, two body, maybe three or so. But the number of terms, if you expand H in an operator basis, will actually be small relative to the size. So making the number of parameters that you have to learn here as a multi-parameter estimation problem in this sense makes it very finite. And this is, of course, the reason why Hamiltonian learning is meaningful and can be done in this quantum simulation context. And the result of all of that will be that sort of step number one. We would like to learn from experiments, and this is a question that many people ask theoretically, of course, during many years now. We would like to learn in the operator context of the Hamiltonian, which is present over here, through experiments by interrogating your quantum simulator here under the assumption of an ideally isolated system. And what will come out is sort of, well, we will learn kind of the mean Hamiltonian, and there will be then certain perturbations over here. The error model, shot noise will appear over here. I'll explain this afterwards in some detail. So what you learn is sort of a family or a group of Hamiltonians that, with an error model over here, represent the learned Hamiltonian. But then, you can take this result over here, and then ask the question, does this also teach us something? To what extent these quantum simulators, have error bounds in the sense of guaranteed error bounds that when we measure the observable over here, that we will also be able to place bounds on them. Hopefully, by just being able to use the learning that we have here over the Hamiltonian, including the uncertainties that we have in learning in the operator basis, all of these coefficients. And at that point, you can take this Hamiltonian over here, if you're able to do that, to a theory simulation, with this error model that we have over here, and compare it and put on error bars. But in many cases, we might not be able to do that. And only have experiment available, and are we then still able to provide error bars on these estimators, maybe then in this regime of advantage, quantum advantage, to do some sort of a self-verification. So in other words, what we want to have is a situation where the quantum simulator not only provides you with some expectation value that you ask for in solving a many-body problem, but you also want the corresponding error bar. So the machine should provide the error bar that you do over here. This is sort of this connection with this.
The analog simulation would be time dependent.
We make the assumption, that's a very good question, that the Hamiltonian is not time dependent over here. We can make it time dependent, but to be honest, they're grounded in parameters. Okay.
But if you make it time dependent, then you also run into like that you want to run
Yeah,
heating.
we can fundamentally make this thing time dependent. We can also talk about heating in the context of adding Liouvillians, which I will do now in a minute. So this is not a complete story, but I just want to motivate here that what we want is this, that we want to ask, do these errors that we learned over here by doing just an experiment, can this feed down here to providing bounds that we can also put an error to this estimator that the quantum simulator provided over here. So we are trying to convert analog simulator to a quantitative calculator that gives us an answer, but also says, that the answer comes with a certain uncertainty. And we want to do it via this Hamiltonian learning. And this is the story I want to tell you, and we are sort of, pretty far, but not completely finished and all of that, but I want to show you the results that we do. It's sort of interesting that in making the connection between the first and the second one over here, there's a paper by Breskin and company, now from some time ago. They have studied error models of this type, so there was no relation to Hamiltonian learning, but so many results in creating these bounds one can actually read in these papers, and this is what we have done. So this is very useful input, what we do, and I mentioned a little bit about this afterwards. So we want quantum simulators, analog simulators, to make quantitative predictions. And of course, what you learn here is sort of like a whole ensemble of Hamiltonians, and talk about what we mean by this expected variable, what an experiment means now in a few slides from now. Few remarks over here. The reason why this works in a regime of advantage is, of course, the old argument that Hamiltonians are physical, k-local, or sparse, so polynomial number and parameters. And of course, we also want to add to the story then that we have noise, we have open systems, and you want to make a model, maybe write down the master equation, but you think it is valid. Therefore, learn also the noise model at the same time that you learn the Hamiltonian. Usually, this noise is sort of small, but but we want to learn it to get a complete picture. Because talking about bounded error without including the noise would be meaningful only for very short times. Let me say a few words about Hamiltonian learning per se, and I'm not going to spend much time on it. There's an enormous amount of literature, and of course I'm aware of the fact that one of the first ideas here that I ever heard about Hamiltonian learning was that we can learn Hamiltonians by creating a single I state, and then this locality, of course, leads here to the construction of the Hamiltonian. Does not have to be the ground state, of course, could also be an excited state if you generate over here. And so this was motivated a lot of people to think about time-dependent dynamics and learning. We are doing here quench dynamics. I want to learn it from that because this is experimentally the most feasible way of doing that. And the starting point is sort of this statement over here that let's assume, and I really say the word assume, that the system is described by a master equation, having the Hamiltonian of interest as the interesting term. And then maybe some Lindblad dissipator sound here. You might ask, does it also work for non-Markovian model, the extreme case being sort of a static noise, the changes from experiment to experiment. And we can extend it, all of that, but the experiment I described below, this was basically laser noise. And one can argue very clearly that this can be described by a Lindblad master equation. But I really want to emphasize, not all noise that we have in experiment is, of course, Markovian and master equations are appropriate, but it is the case. And then sort of the idea is this thing, well, we want to learn now this Hamiltonian from experimental data, and we make a certain operator ansatz, like the superposition of St. Pauli's in the string model that we have over here, or then very similar that you have here jump operators in the Lindbladian. And we want to expand all of that in some operator basis and sort of go up to the point where you can see that higher order terms are not only physically unlikely, but you can also see in the experiment that they're very small. But the goal is now to learn these experiments, these coefficients over here. From experiments, that we sort of try to compare with this master equation, therefore extract these terms. At the end, we're going to use these Hamiltonians and Liouvillians to make them predictions both on the theory side, but also the purely for measurement regarding this bounded error. There have been experiments, but actually not too many before. Here single qubit moving at 5 qubit experiments, very impressive, 300 fab ions, but for very, very special Hamiltonian. Lumin 1 did this a year ago at Chihuahua. Learning this Hamiltonian and these coefficients, we will see that we sort of are learning non-commuting terms in operators, and I think that's essential for the story, and including also the dissipation following. So I just have one slide on the basic way how to do that, because this doesn't really need much more. The rest is really the technicalities. If you write down a master equation, you write down Ehrenfest theorem, you take any observable over here. Of course, an experiment would know, what the value of this observable is at time 0, but also measure this thing at some later time t that you want to choose. And there's different possibilities, maybe even many times. And clearly, this thing is then given as this, commutator of pole with the Hamiltonian expectation value. I can see that if you have an ansatz over here, you insert it over here, you're learning sort of, you will measure the experiment. Now, correlation functions, and these coefficients c that we have over here, they will sort of appear out here as unknown, and in the end show up with some cost function that you would like to minimize when you do your regression and trying to find the Hamiltonian, which is most consistent with the experimental data. And on one hand, this thing over here, but on the other hand, also this correlation function over here that we use this kind of integral here. And also then here for this term. So we make ansatz over here, we get a system of linear equations. You have to ask, what kind of an ansatz and what will happen if you improve the ansatz more and more. There will be shot noise, there will be, the ansatz will at the end maybe not despite the whole thing because there's additional terms. But the way how we do that is this, that we do this experiment, preparing different initial conditions. In our case, there are 3 sets that were taken, doing the measurements here. This is a tool set, this is really high quality. There's some estimation of these integrals. And maybe the most interesting part is this, that we do then this sort of ansatz assessment up here. When you do this, you collect a lot of data, actually taking randomized measurement. This allows us to work out many correlation functions when we need them, later on, because we can have these high order correlation functions. And when you plot the error over here of this Hamiltonian and Liouvillian learning as a function of the number of runs, of course, you can see that if you take the number of runs very long, the unhappiness of the experimentalist increases, I guess exponentially over here. But, so there's a natural cutoff over here. And you would like to then choose an ansatz very often by reparametrizing. It's similar to I don't know, principal component analysis, machine learning, and so on. So if you make a certain ansatz, you will typically have this scaling, and I'll show you afterwards an example, where as a function of shot noise, you know, the accuracy where we learn this assessment of the error goes down, and then it will go over to a plateau. And the plateau means that, well, maybe your ansatz you had over here is sort of incomplete. It tells you that you should increase additional terms, or maybe reparameterize. And the better ansatz is the one where this knee that you can see over here from the shot noise going over to this plateau happens then sort of further down here, because this is the quality how you learn your corresponding Hamiltonian. And of course, we would like to find an ansatz where we go down as long as possible here with a given number of experiments or data that we have available, you know, until this plateau comes. So this may be a machine that you don't see it anymore. But that's sort of this learning of this error model that we want to do, and similar for the Liouvillian. I show this plot just to tell you that we've done it for 10 ions, and we're showing our result for 10 ions, but these things also work for 51 ions, but I'm not ready to show you these founded error things in this case. So here we still have to finalize our analysis there. The typical result, you know, we sort of expect that there's an XXYY model in our Hamiltonian with some long-range interaction. Here it tells us that this is a power law, but there's some deviation like exponentials that people normally don't discuss, and there will be some transverse fee. This has to do with also laser detunings and all of these kind of things in our case. And we take a model like collective dephasing, which turns out to be global laser fluctuation, which is the dominant term. And then we, of course, we go over here and we add additional terms to investigate, are they there or not? But it turns out that actually this ansatz, which is what theorists would write down immediately, would sort of contain all of the physics, but we want to learn these coefficients. And you might say, well, they will be approximately translation invariant, but usually they're not. So very often these ion traps are a little bit misaligned. And using these techniques, one actually finds bumps, you know, in these whole structures that are not entirely obvious. But just show you examples over here. So when you take this JX over here and we do this learning, and this at the end is something like a few thousand parameters to be learned here, you can see this algebraic decay over here from this long-range interaction, and then also for the other ions here. And drawing here also the corresponding power law that we would expect. One would expect deviations down here from that, and there's some indication, but we can argue about that, similar than for the efficiency Y over here, sorry. Here's sort of the local magnetic field that should also be constant, but this is sort of what comes out over here. And you can see the last term over here, this is the collective dephasing that we learn. So this is the learning of the Liouvillian, and we find this status emission terms actually so small that we could not really significantly solve it. But okay, these are all of these, you know, different interactions that are listed down here, and we learn all of them in parallel in this kind of an experiment here. Just one more thing that I said before, well, we can do this error assessment of the ansatz in the form that, you know, when we do this analysis here for the full ansatz, which is an which is an XY model, plus a magnetic field, plus a dephasing, and we make now this plot of this error assessment. You can see a shot noise of a very long reach. This is the deep shot noise over here. You don't see a plateau, but we can sort of introduce a plateau artificially. We need more measurements over here to find a plateau in these higher order terms. But as I said, there's a natural cutoff in terms of lifetime and graduate students, I guess. That when you take, for example, an ansatz where the C terms are missing, you can see that the plateaus develop, and even more so when you leave out the YY term, you can see that the whole thing is completely flat. So by analyzing this convergence with the number of shots that we get over here, we get very clear hints what kind of terms are missing and so on. In our case, the conclusion was that this was a fantastic good model. Okay, I just show you results of theory, experimental correlation, and then you can take this Hamiltonian that we learned, this small system here, and compare theory with experiment. This is sort of the learned Hamiltonian over here, these bands. And then you can see experimental data over here for this bench dynamics. And then we sort of show now more results for the talk now, introducing error bands. So I have a few theory slides over here that I will go over very quickly for the very simple reason that doing this thing here is sort of it provides us the framework. I mean, this paper by Breskill explains a lot of the mathematics, behind that, and we can take it with this different interpretation over in our context. But I just want to explain very briefly, what kind of things that we care about. So when you do Hamiltonian learning, you have here the operator that you learned, as a Hamiltonian H, the most likely one that you have, the best guess, the 2 Hamiltonian. And these V's over here are the uncertainty that in the Pauli basis you might expand like this. This is sort of the mean coupling over here. These are these couplings over here that can be described by a Gaussian noise model that we have here with 0 mean. So this is Gaussian statistics here, reflecting the uncertainty of the learning. And what bounded error the certified quantum simulation does is that we want a computational device with a guaranteed performance. Okay, this is sort of not normally how analog simulators are discussed. So the goal is to compute an expectation value O, where I know the Hamiltonian with some uncertainty. I can measure the device this operator O, and the machine also tells me at the end the error model, but this error, but also then in the second iteration. Then it allows me to provide errors only from analysis of the machine. So machine gives the answer. So the ideal combination device would correspond, well, this is the mean Hamiltonian, so the most likely one. And you would say, well, if I want to do a combination of this device, I would say this O of T over here, this is my operator, my observable. If it evolves according to H, that's the quantity that we really want. That's the quantity of theories we like to have. Given this Hamiltonian, this is what we'd like to have as an answer. Okay. But now you can ask yourself, in a real experiment, is how the like drawing from this ensemble of Hamiltonians, within this error model over here, one of these Hamiltonians, and then looking at the time evolution, H prime, for that. And so it gives you different observables, and you want to compare the expectation value of your observables, that you see in the experiment, with the ideal prediction that the theorist would like to know, based on, well, I give you H, and then I would like to know what the answer is. And so can we now use this analysis of these error bounds, in order to make these quantitative predictions down here? Can we bound the error from either then knowing the error model and with theory simulation, or then one step further doing experiments alone? And
bounded error on the scale of order 1 amount.
You will see now in the following sense. Okay, so we will be able to do that for the machine only time for not too long times, because we need to write down power series expense where the machine then measures higher order correlation functions, and there will be, of course, we talk about short times, always something like the Reed Robinson bounds, that we help us to provide the natural cutoff. And to be very brief, we want something like a bounded the expected error, that you have your whole ensemble, and this is sort of what you measure, the expected error, and the bounds derived, essentially by Breskill, and we can measure these things now from Hamiltonian learning over here. And bounding the distance from the mean trajectory, again, there's error bounds over here, and on the right-hand side with all of these constants, and we not do that. The main conclusion is sort of this, that at the end of what this whole thing leads to is this, so you can say, with the probability so-and-so, maybe 95%, you can guarantee that if you do an experiment that measures now a certain observable, that the theoretical one that you wanted to have for the Hamiltonian H, is bounded by some quantity delta over here, and at the end, the machine, the Hamiltonian learning provides you, what these quantities are here. If you do that, these error bounds are not very good, so we improve these error bounds, by doing perturbation theories and then to some higher order, where all of these coefficients could be measured on the real quantum machine. So there's a lot of technical things in here. But let me just show you what we have. So on the left-hand side, this is again an example where we take a predicted observable and take the Hamiltonian that we have, the predicted Hamiltonian, and we take our error model and we simulate these things classically. And we will say that everything is essentially within the error bar. It only appears like this when it also include the Liouvillian. And this is sort of a result over here. Quantum simulator provides the error bar only from the experiment. These are these Breskill type error bars, adapted to our case and actually improved by the way how we do it, measured on the machines. And these are sort of the real errors that we can, that we know from the real, because we're still able to simulate over here. So these error bars are pretty amazing. Satisfied, you might say, well, the error grows with time. Yeah, this is true. But that's sort of what we are at the moment. But I guess it is the first time that analog simulators here provide, bounded error quantum simulation in the sense of being able to predict quantitatively And it would be great to do that, of course, then at the end for bigger systems, it sort of works for 15 particles over here, then at the end. But then also to do that in the regime of quantum advantage, where these techniques, principle applied, but doing that is a story by itself, of course. But to see more examples, here theoretical simulation, I just want to show you, this evolution sort of left to right. This is experimental data where you do only Hamiltonian learning and don't include the dissipation. These things are off over here, but otherwise we are pretty well within this error bands over here. So there's really a complete consistency, and you can also then plot error bounds down here that I'm not going to discuss. There's a lot of no technical details over here. Yeah. But you can see what the basic ideas are. It is sort of that we have a black box machine, despite the Hamiltonian and Liouvillian, and we would like to get then bounded error expectations.
So does this technique still work when the device is biased, right? It's like improperly calibrated or if there's noise or something, and like you don't understand
what we do is simply that, we prepare product states and we make measurements. So we assume that these are almost perfect, and they are in terms, there could be span, state preparation and measurement error and the whole thing. They're very small in these devices over here. They don't play a role on the level that we talk about here. But this is really interrogating the machine as a black box. So we're not talking about calibration or whatever. I mean, of course, when you measure time there, you have to know what the time is, because all of these units that appear, these weights are then in the measurement how you accurately know this time. But otherwise, there's no assumption. This is really treating the whole thing as a black box, and it tells you my Hamiltonian is this and that within this error model that I discussed.
But you want to compare like the Hamiltonian that the experiment is realizing to like some theoretical ideal, right?
That's right. So if I'm a theorist, I give the experimentalist the Hamiltonian and ask, for this Hamiltonian, can you do that? And well, when the experimentalists come back, I have an analog simulator, I might not be able to realize your favorite Hamiltonian directly, but my analysis of Hamiltonian learning gives me this Hamiltonian is the most likely one. And then I give you these uncertainties so that it's a whole ensemble of Hamiltonians with a certain probability distribution, Gaussian, reflected by these error bars. And when I say that, okay, so I take the mean Hamiltonian, the dominant one, is the one where I would like to know the observable, that based on the analysis of noise, I will be able to get out what then the corresponding error would be on the observable that I want to compute.
And presumably there's some like triangle inequality or something that lets you relate that to like the theoretical ideal that you're trying to model in the first place.
Yeah. One more question? Yeah.
Yes, so in this model, you imagine that there's one set of these coefficients for the error Hamiltonians, and they don't change over multiple experiments?
Well, okay. I think you bring up two things. So in principle, what we do here is that we write down an ansatz, because I go in there and I trust my friends that they do this XY model with a magnetic field. These are my zero order ansatz. I go there, and this has the prior knowledge that I trust the experimentalists that they have not done something crazy. Again, of course. Never do that. Then we sort of add additional, then we want to learn these coefficients, but then we add additional terms to the whole story, testing for maybe higher order Pauli interactions, and there may be many of there, and we try to explore them. And we can do that by classical post-processing at the end, and real parameterization. So that this plot that I showed, you go down with the shock noise, and then you see the knee. Once you see a knee, you know that you are limited with your ansatz, and then you can try to improve it, your parameterization. So there's a classical post-processing part over here, which gives that.
Yeah, my question is just like over many experiments, you're trying to learn.
Oh, okay, you're saying okay.
one set of these coefficients. This error model.
Let me emphasize over here. We make the assumption that the Hamiltonian is constant in time. We also mentioned that before, But second, of course, you're completely right that in an experiment there may be a drift. Okay. And in principle, we can include these drifts, and in some experiments, where the machine is used one day to do that, another day to do that, we see clear discrepancies, that there was maybe a drift by turning the machine on again. We can in principle include these things over here, and but this set of data that I showed here, like the one, was it now? Okay, that was giving us, this going down with the shot noise, and then finding that we really find that this thing goes down like the shot noise. In some early experiments, you could see that this thing was bending over, and this was an occasion effect with the kind of drifts that we had. And it may also be the case that you got a static magnetic field that is changing from run to run. I cannot model it with a master equation, but we would in principle know how to include that. So you're right that these things should be included, but in our case, there's sort of the arguments why these things or the experiment is done in a way that hopefully this doesn't matter so much. It seems to be consistent. Okay, thank you. Okay, and let me now tell you briefly about this inverse quantum simulation. I will do this very quickly because it's sort of more an idea that there may be more on this Hamiltonian learning, and I think it is actually a little bit along the lines, can quantum simulators also be useful to do something? And this is work together with Pitt and Cockale and Brazil, my student at Harvard now, and actually Pasha, who has joined this project and makes a fantastic contributions. He also called it jokingly quantum material design, and we'll see in a minute what I mean by that. It is trying to find relevant applications in quantum simulations. We live in times where it should be useful or relevant, so we do that here. So again, standard quantum simulation experiments work with specifying input Hamiltonian, like we are trying to Hubbard models, and doing maybe a Fermi Hubbard model over here, measuring a phase diagram. You would like to see D wave. This is what theory sort of predicts, and then fulfill the ultimate promise that we always said we are going to simulate ITC, on a model like this, a model system like that. But then, of course, what might happen is that an experiment does not discover that. And but then you might say, well, we just had Hamiltonian learning, so why not check if the Hamiltonian is really the one that we specified over here? Maybe they haven't got the Hamiltonian wrong, but microscopes and all of these things you can do that as the Hamiltonian learning story, which I told you. But you might also, and then maybe this hopefully, certainly actually will be okay. But then you would like to do now, and if we call this thing now inverse quantum simulation, you might have the idea, why not turn quantum simulation around, okay? Maybe some of you would like to draw a phase diagram or specify, a property that we have over here, like seeing a D wave, or maybe also some susceptibility could also be very big. You would like to design materials, that have certain properties that we specify, and sort of do this thing around the way around here, that you have a Fermi Hubbard experiment. But now what we're doing is, the case of D wave would be to write down a cost function where you would like to optimize, and would like to see D wave for the parameter, very large. So let's write down a cost function. We run maybe a variational algorithm on this Fermi Hubbard simulator that we have over here. That can be programmable because of some digital mirror devices and all of these nice gadgets that we mentally have now today. To optimize the cost function, then you would know, well, I got now a wave function over here in my device, and I want this to be the ground state of Hamiltonian, but I would like to learn the Hamiltonian, because if I have learned the Hamiltonian, I would know what kind of material I would have to construct to get this desired phase diagram or these particular features that I'm optimizing over. So we can see Hamiltonian learning sort of gives now here the Hamiltonian out, and it's really going backwards, and you specify properties, the cost function, have a quantum machine that does it. D wave is sort of one example, and then you learn the Hamiltonian back. And of course, you want to learn the Hamiltonian that is now learning from the eigenstate, a Hamiltonian back, but of course you want this to be at the ground state of the Hamiltonian. We had here a cost function where we try to incorporate this, but Savovazio came up with Hamiltonian learning techniques where you learn the given wave function according to this Stanford protocol here for single wave function learning the corresponding Hamiltonian that guarantees it to be the ground state. I mean, this has not. There's some difficulties here and there, but basically this is what's achieved. So you can apply that over here. And I just want to give you one example that's something that we can still do in theory, and of course we can do 2D, but then we don't have the quantum machine. We cannot do that theoretically. You might say, let's optimize, just on the ladder system here for the D wave order parameter. And what you get now in different operations of different depths of these variational circuits that we write, it tells you more and more. If you want large D wave, the D wave parameter from here to here increased by a factor of about 10, because we were optimizing that. You learn the Hamiltonian back, and there's a very simple message. If you add cross currents, the square lattice, and if you read off some of these flat iron papers, you know that, of course, you will get them, know that this enhances, of course, the existence of the D wave phase, something which is known theoretically in this context, but this kind of learning, inverse quantum simulation gives you that. So the obvious question is, can you also optimize for ITC or something like that? And there's some results that indicate that it's sort of interesting, but there's no final word spoken. This is a project that we've been doing now for some time, but I think it is sort of inverse quantum simulation and quantum material design is interesting. So I'm now going to the second part of my talk, and I see that I've spent already too much time. So I'll try to at least get across the main message, which is quantum metrology and quantum information. And I want to say a few words about the project that we are doing at the moment with Charles. He's a student borrowed to me from Hannes Bichler, and Thorsten Sacher has been a Lattice Gauge guy, and Denise Basilia is our quantum metrology guy that works with me, and now is in another postdoc appointment at Innsbruck. And maybe I should simply call it a little bit provocative, and I have to explain that, of course, emulating atomic clock interferometers with quantum networks, and a lot of these things have been motivated in the discussion with Junier. Chila has this Q-sense, where people here are partners of, and so they're the ones that make us think about, the interface of quantum information and quantum metrology. And of course, these things are interesting in the context of general relativity. We have here atom interferometers, like, are being built here at the house in an amazing way. And when you talk about the atomic clock interferometer, we have, of course, this internal two-level system. So not only spatial superposition of atoms here, but also redshifts, like in the gravitational field of the Earth. Of course, you would like to do that at the end, in more non-local way. And can we emulate that on something like a quantum network? And by quantum network, I mean over here that, at the moment, this community is building fantastic quantum networks basically for quantum communication. And can we benefit, in the quantum sensitive context by sort of using quantum networks to make interesting measurements? And I call it here provocative. Can we emulate an atom interferometer over a very much larger distance, the quantum network over here? And you will say, in what sense? I mean, the answer will be afterwards yes. It will be not the one-to-one correspondence, but hopefully I can convince you it's kind of interesting. I should say that this idea, I know we've worked on this for a time, there was a recent paper in the archive by actually Beauregard over here, and Zukowski is also me a well-known person. I'm working on the interface of quantum and GR and so on. They wrote a paper, and they also brought up this idea. So we're a little bit late in writing up our paper, which is not out yet, but you will see that we have a different story, and I want to tell it to you, but I want to point out this correlation with this over here. So quantum communication goes quantum sensing. Okay, we want to go to large distance entanglement, and we want to have this gravity quantum interface. And at the end, what we're going to do is to do non-local ramps interferometry, and I want to include the variation quantum circuits in the whole story. So we want to have quantum networks and variation quantum circuits, and we will identify the cost function, what we want to optimize now in the following discussion. Of course, the story goes for me also back to discussion with Junier. We wrote this essay here in the POL about that came to the conclusion that the rapid development of quantum information science is going to define and advance the frontiers of measurement physics. And I think that you should see this whole study basically following that. And of course, we have all of these great machines like quantum simulators and so on that provide us now tools for actually doing that. But I talk here in particular now about these non-local quantum networks that are sort of not included directly. Before I come to that point, let me remind you that a few years ago we did this prior work on variation quantum algorithms to find optimal quantum sensing, and the discussion was to do a ramp interferometer. They have an entangling input gate over here, and you have some decoder over here that does correlated measurements. And using resources available on the quantum machine, we were asking over here, how can we optimize, with the given resources, representing this as a variational circuits, and one over here, the performance of this, in this case, single phase estimation that we have here. So what you do in order to do that is that you define a metrological cost function that contains all of the wish list that an experimentalist might have. Of course, the first one will be signal to noise ratio. In the particular case over here that we have studied, it was also that we want the noise not to be only low, but we also want it to be dynamically very broad for a big range of the phi over here. And then you optimize, this cost function, the metrological cost function on the classical device, feeding back and forth. You can do that on a machine, even in the machine where you cannot calibrate your gates over here. This is very important, the diodes. So you can see a connection between the programmable quantum simulator and the programmable quantum sensor, that to the extent you're going to extend these ideas, and also the quantum sensing networks. Find sort of very short circuits that you can do with high fidelity that get you close. In this case, it was actually very close to optimal. I always like this to show this picture over here. That was sort of the main result. When you have here an interference range, and down here you plot the noise as a function of this dynamic range. So these are the bases going in here, and you want this noise to be as low as possible down here, and we ask the machine, find the best solution, input state, and also measurement, which is as broad as possible in this regime over here. When you do here product states, you get it over here, and now we want to improve. This is coherent spin states. If I make this in a squeeze spin state, which is optimized to bring this down over this dynamic range, you can see the noise going down. It's very good. But then you can also see if you do the measurement circuit only that you optimize over here, the range gets actually broader. So this is no longer a sine function. This is more like a triangular ramp that we have over here. You can see this thing becomes very broad. And when we sort of combine both, you go to the red curve. So this machine has found itself, from the short circuit, but if we build out of the available resources here, we are very close to practice optimal interferometer that quantum mechanics allows from resources like one-axis twisting that was available in the half-time experiment was over here. So this sort of indicates that these variation circuits, are maybe more like a hack, but at the end they work fantastic in improving these interferometers very often close to the quantum limit. And then we had, of course, and this is now the discussion that leads over to this sort of maybe more gravitational things, publication with Anna Maria and also June, that was exploring the dynamic interplay between mass energy equivalence and so on. I'm not going to explain now these things here in detail, but sort of the goal was here to see the gravitational redshift and the scale of an optical lattice, but June does this in an amazing way, like this millimeter distance, Korkovitz, these great experiments also here. But the challenge is usually that, well, we should build not only for millimeter spacing, but we would like to go to large distance, sort of covering many kilometers or whatever, And we know how to build quantum repeaters over many kilometers, and so can we benefit in running this thing as a quantum sensing network. Innsbruck has experiments, we have this 230-meter quantum link that makes EPR pairs, and I think very soon this will also be extended from Innsbruck to Vienna. And I saw a paper in Nature today, they talked about 250 kilometers. So we know how to get entanglement, over a distance in a phase coherent way. This is sort of the status at the moment, but we would like now to take these networks and use them to run now maybe quantum metrological protocols are interesting. So coming back to the idea over here, well, if you have a standard atom clock interferometer, I mean the following. The atom is first of all split in terms of its center of mass between, I'm drawing the Earth down here, between some lower gravity and the higher gravity, but this will also be at the end, some other gravitational field here, giving rise to the Newton gravity over here. But of course, due to the fact that we have an internal state, the dominant correction from GR would be the so-called redshift, which turns out to be tiny, and basically would correspond to the effective mass difference between the bound state, which is the excited state, and then we have the ground state down here, and the excited and ground state having a different mass. This is of course reflected, and then as a correction where you see this as a difference in the corresponding energy of the two-level system. So this has external degrees of freedom and internal degrees of freedom, and there's been a lot of proposals along these lines, and of course I'm aware about the atomic interferometers that are being done here, very much so. We want to sort of emulate this, at least in spirit, explain it to a many qubit internal state only entanglement that we can run on a quantum network for hopefully very large distances. And I said that this idea has also been now mentioned by Beauregard. So we started not knowing these things, but in the meantime, there's a paper out that also talks about that. So it comes really down to, can we probe non-local mass superpositions, and do we have the tools right now in the lab to actually achieve these kind of things? And how do we get these redshifts that are really tiny over here, sufficiently large that we can do that? And of course, when you go large distance, the plan is to go over 30 meter height, but to make a quantum link and do something like that. And this takes principle possible. Here's some slides about redshift that I don't want to go in detail. The statement is simply valid if you're excited in ground state. There's different masses, and we'd like to see this mass difference here. But of course, first of all, there's some Hamiltonians that you can write. I'm going to skip this over here. What kind of knobs do we have to change this redshift? So first of all, we can turn it off, because if I have an optical transition here and I bring this up or one down, then you can see the redshift is basically negligible if these states are essentially degenerate, like in the ground state temperature. We're going to use that. We can enhance the redshift by using n atoms, then you get factors of n, of course, in front. And so we would like to work with large ensembles or large quantum simulators, but we will need entanglement capabilities that I will describe afterwards, but I guess that they are available. So we want to engineer non-local, that's important word, large mass superposition with atomic ensembles. And of course, at that point, I think of the thorium clock that Julieta has built and these possibilities of being going to feed electron volts that I've read in this nature paper. There's a very promising way that we can talk about much larger masses than we have at the moment, but that's only sort of the side comment. So what do we want to do? So the experiments we have in mind is like the one that these people over here built, where we have Alice and Bob, we have ensembles over here, atomic ensembles. And this community has shown us experimentally, and we have done a lot of theoretical work along these lines. So getting entangled states between these atomic ensembles over some distances underlies the quantum repeater ideas that we had proposed. It was now realized for large distances, from a few hundred meters to even many hundreds of kilometers now. And what does a quantum repeater actually provide us? A quantum repeater says that we have here basically two atomic ensembles, okay? And we generate here states where these ensembles are, one is in the ground state, the other one has one excitation there, over here, and also vice versa, okay? So this is a non-local Schrödinger cat. And you can see this non-local Schrödinger cat is actually very, very small, okay? Because this effective mass difference that you have is really tiny, Julieta can detect these things. So the first thing that we're asking, and this is now the room for the variation protocol, is this: that can we now make here mass superpositions that are not only one excitation, but maybe many. So we would like to create here a state that somehow grows, and we have many excitations, and we're going to use variation circuits for that. So this is making the cat that we have over here sort of bigger. You have to do a non-local gate on that, and since this is generally difficult, we're going to use some variation circuits that give very good results. So we want to do mass engineering if we want. We have sort of, here, this corresponds to a mass and none, but then we have excitations in the system here corresponding to a different mass, and by exciting many, of course, will increase its mass, and that will make it easier to detect, while we create this very non-local TPR-type correlations. And of course, you might also do things like, I got this thing in the ground state, whereas the other one is in a superposition of, a few atoms excited and then maybe many atoms excited, corresponding to different masses. So we can make here mass superpositions and we can engineer them, not locally with our variation. Engineer large mass superposition. This is sort of what the goal is. Well, the experiments we have in mind is sort of like neutral atom clouds over here, or maybe also trapped ions. And if there's only global addressing available in the systems, you can see that we have here a situation where you work in a symmetric subspace. This is the ground when all atoms are down here, they have a certain mass, and then we start exciting them to these different levels, they correspond to different masses. So in this sense, the usual quantum number m that we have over here will also correspond to masses that are one mass is down here. Now we can discretize the mass going up here and engineer basically any mass superposition that you want over here, and then use this as the interface to the interaction discussion. There have been these experiments discussing one-axis twisting, and we're going to use it as a resource. So when you run now on the quantum network over here, a variation protocol, you would like to grow the seed state that has only one excitation to something that has now many excitations. So the challenge over here in doing that is basically that you would like to apply now local dualitaries to the whole thing. That leaves the atoms are down here, or Bloch sphere, down here, the ground state, and this one excitation corresponds to a ring around this thing. We would like to move these rings up here, maybe even split it up and get a general mass distribution from this whole thing. And can we do that with local operations? Well, for variation, you can do that, and also for the second case down here, let me just entertain you by showing you a few results. So for one atom, this is tiny. Let's make a Bloch sphere representation. You can see that you cannot see the one excitation over here. It becomes visible if I look at the Bloch sphere from below. Here this is really the ground state, and then one excitation, just this Wiener function ring that you can see over here. This would correspond to a mass distribution, where it's just the one mass here and a very tiny redshift single atom mass, then this is the mass distribution of the second one here, plus the Schrödinger again. Can we move and do that? And we can do that, and for example, we can also do that and for the two excitations over here. For example, this is a block state virtualization where we get two masses over here that we want. This is the ideal one. And now we can do that, for example, for variationally. You can see that on the block sphere, this looks pretty flatty, but if you project this thing onto the mass, you can see very clearly that there are two mass superpositions over here that we can just engineer with a very simple 5-layer variation circuit that we can optimize in your quantum sensing network over here. So what physics do we want to see? Well, we want to do non-local ramps interferometry, that we create entanglement over distance at the very beginning, then we would like to grow these heads, the way that we said, we initiate these smart superpositions, and then do in this case the very traditional redshift. And I just want to show you why we're interested in this. So just our book now is in Vienna, one of sort of the counterparts in the Vienna IQOQI Institute. They've thought a lot about this atom clock in the front over here, and wanting to see the redshift. And what they see is basically these superpositions that are defacing over here. You got two frequencies, the one of this redshift and the one that you have from the Newton gravity down here, and then of course also the revivals. And this is a kind of phenomenon that we also want to see here. This is related to this discussion of universal decoherence. This. So we want to do that. We need this over here by making these superpositions, and I just want to show you the few results that if you do one mass superposition, this would be sort of like emulating an atom interferometer, the way that I explained it. Measure the corresponding redshift by this non-local ramp spectroscopy. This would be the variational part, clearly showing this sort of frequency, the same here, theta is different. This would be a 2-mass interferometer, emulating this atomic clock interferometer. This is the variation over here. This would be, if I make a coherent superposition of mass states that are up here. You can see that this is sort of opening, I guess, an interesting playground if you have a quantum sensing network. It works at the limit required over here. These are the experiments to be done, and this brings me to my conclusion here. Talked about quantum simulation, didn't really mention the lattice stage part, but I've told you about bounded error quantum simulation. I've told you that I see an interface between quantum simulation and technology. Also, in the sense of using, for example, these variational circuits to achieve certain tasks that are interesting from the quantum sensing point of view, like on the network here to go, for example, Schrödinger at superposition, and mass superposition. Thank you very much.
Thank you for the great talk. I'm just wondering for the quantum metrology part, so like some of these tracks, they also have like multiple most. Do you think you can take advantage of them? Yeah. So like, do you think you can take advantage of that to like basically they spend logical protocol because they are really low frequency, but principle that they can long coherent.
I think that you're completely right. The experiment that you are thinking about the use of the bites are completely higher. That's exactly what I was emphasizing here that I like quantum ensembles because they're much larger than the particles. So in this sense, the potential to mass difference large, sort of different force, microscopic, whatever microscopic means here. So the opportunity is also. But you can really take your favorite system, run these corresponding variation algorithms, then you find optimize the cost function to find what sort of thing that given the particular setup. So you're right.
Yeah, on the topic of the bounded error quantum simulation. So if you're trying to match like some given Hamiltonian without any dissipative terms, how sensitive are you in your bound to the strength of your Liouvillian terms relative to your Hamiltonian terms in terms of actually matching some theoretical Hamiltonian that you're trying to study with the experiment? So basically, how sensitive are you to the fidelity of your experiment not being maximal with respect to actually being able to bound your error with respect to some Hamiltonian?
Okay, so I mean, of course, the story that I told is this, that we take a machine and we learn the Hamiltonian, which is the dominant part, and also the dissipation, which we don't want, but it's there, that we're learning the error noise model. So at the moment, we are including additional bounds. So what the quantum simulator does is that it really simulates this thing for both the Hamiltonian and the Liouvillian. And what you're asking, can we sort of subtract the part from the Liouvillian to do some error mitigation in this sense? This is not what we did over here, but I think it's an interesting thought actually. I should think about that actually more detail, how we can take sort of this error out. We added additional, for us, this Liouvillian at the moment appears in the error bound, but sort of we simply say the simulator gives that and the dissipation. You're saying we should include the dissipation part. Now there's a feature, but there's a bug that will sort of correct this error. I think that's a good point. Yeah.
For this last section, can you say something about sort of how macroscopic this superposition state one needs to maybe compete with alternative approaches where you're actually, say, doing atom spectrometry or I guess, yeah, sorry, I'll let you, yeah.
I'm not an atom
Yeah.
expert.
Yeah.
But I would say that they sort of go in different directions. I mean, atom interferometry is, of course, amazing in the sense that the separation out down here, can at the end become very large. But we really have in mind here to measure distances that are in the distance that atom interferometry will never be able to do, and sort of then use essentially quantum communication tools that were developed in order to do that. So I would say they're sort of maybe complementary. We go to very large distances. This thing here goes to very large distances. The consequence is that these redshifts are really very, very tiny, so we can only compensate it by a very large number of atoms. So I would say that they explore very different regimes, and I don't see them directly competing. I'm only saying that on the level of this atom particle performances, what Junier has done with this millimeter, it's just amazing in my opinion. But at the same time, it would be also important to go to these larger distances, and this may be achieved by the tools that we have. This is really doing an outlook Ramsey, where in this Ramsey we see that there's an atom over here that has a redshift, but this one not, and we have a Boolean superposition that is greater. We actually have to pick it, so it's active by using different mass superposition, so it's kind of a different. It's opening a slightly different door.
Maybe related to that, is there any fundamental difference between using the internal state and using an actual change?
That's a very good discussion. These things in all details, it's a massacre in all discussion. I would argue fundamentally not, but in practice there's a lot of it. Fundamentally not, in the sense that if you look at the eyesight equation, the right-hand side, you have this energy mass answer, this so energy is equal to the mass. If I take a single atom and it has a mass, and I take an atom with a pointer, that you sort of now different cases here, and I don't see the pointer. There's a difference between one atom, there's excitation, an atom is either here or here, so the mass is here. And here we have more like we have a certain mass reference and not these atoms in the graph state, and then we build excitations on top. So I would argue it's sort of very similar. Is it completely identical? Then we can depends on your how. But it's very interesting. I think it's very interesting.
Is there something fundamentally better about this experiment with non-local entanglement than just taking square the number of atoms and locally having a macroscopic atomic clock at the two places and measuring the amount of time that evolves? I mean, right, you're just measuring the redshift just shows up as different proper time for the observers.
Okay. So what you're saying, I think, is very important. This is exactly the question you asked about. Why the hell is this interesting? I think it's a this applies to many things that we do. But I would say, well, people have seen redshift, in the 1960s by classical measurement here. Then you find it in an airplane and comparing it on the classical level. I think what I find interesting in the context, so this is added by these kind of experiments, is that we explore at the same time something that all of us will say, and the answer is kind of obvious. We're making here, non-local spatial superposition, big Schrödinger cats, and we see them in interface with gravity. Do I expect any deviation from, writing down the Schrödinger equation for space-time? This makes predictions, and of course, there will be superpositions and coherence and all of these things there. I don't expect any difference, but it is one of these things that I guess should be tested. You know, it's like the discussion of Bell inequalities. These are the higher foundational level. You know? Like Bell inequalities, where all of us would say, well, if no quantum mechanics is the outcome, so why should I keep this device? But I think it is also true by making an experiment, you know, non-local superposition and seeing these revivals, you know, and so on. That I think would be interesting. If you discover something new, probably not, okay? But who knows? I mean, this is the reason why we do many of these things.
So the question is like, okay, we get this prediction from just thinking about general relativity as classical and quantum system separately,
Yeah.
and then if you actually have non-local entanglement, you get the same thing as just
So we would expect that you know the answer over here. But to see that in an actual experiment, you know, that is kind of a macroscopic entanglement over distance in the interface with GR, would be an interesting question to ask. But I don't expect any outcomes at this level, but no, it's a first step.